So, let us look at some examples. So, you take n equals 1 and you take omega equals 0 1. So, you have the problem is minus u double dash equals lambda u in 0 1 and u of 0 equals u of 1 equal to 0. Okay. So, multiplying by u and integrating, you get integral mod u dash square 0 1 equals lambda integral u square. So, this implies that lambda is strictly positive. Okay. So, then if lambda is greater or equal to 0, but if lambda equal to 0, then you get u dash equal to 0 implies u equals constant, but it vanishes at the boundary points, and therefore that implies that u equal to 0, and that cannot be an eigenvector. So, lambda has to be strictly greater or equal to 0. Okay. So, in that case, you know the general solution u double dash plus lambda u equal to 0, lambda greater than 0. This implies the more general solution is u of x equals a cos root lambda x plus b sine root lambda x. This is the general solution of a second order ODE. Okay. So, now you have u of 0 equal to 0, and therefore, if you put x equal to 0, this term will disappear. Cos root lambda is there, lambda is not 0, cos 0 is 1, and therefore, this implies that a equal to 0, and therefore, that implies that b cannot be 0 since u is not identically 0. Okay. So, u of x equals b sine root x, and then u of 1 equal to 0, and this means that root lambda must be n pi. Therefore, lambda equals n square pi square. So, the only eigenvalues of this problem are n square pi square, okay, and the corresponding eigen functions are some constant times sine n pi x. Now, are there any others which we cannot, because this is we know from the Fourier sine series that root 2 sine n pi x n equals 1 to infinity is an orthonormal basis for L2 of 0 1. In fact, you can so this is the Fourier sine series, but you can even prove it otherwise. Suppose you have that f is in L2 with integral f sine pi x n pi x 0 1 dx equal to 0 for all n equals 1 2 3 etc. Then extend to minus 1 1 with as an odd function. So, you just put f of minus x is minus f of x, and therefore, so f of minus x equals minus f of x. Okay. So, then if since sine is also an odd, so integral minus 1 to 1 f of f sine pi n pi x is twice integral 0 to 1 f sine n pi x, that will be 0, and then integral f minus 1 to 1 is also equal to 0, and integral minus 1 to 1 cos f of cos n pi x. Now, this is even, this is odd, and therefore, that is equal to 0 for all n, and therefore, from the Fourier, from the Fourier series, you know that this implies that f equal to 0, and therefore, that shows that the sines form a complete orthonormal basis for L2 of 0 1. And therefore, there are no other, because you know from the theory that the eigenfunctions form a complete orthonormal basis, and therefore, all the eigenfunctions, eigenvectors and eigenfunctions are given only by this set. There are no other solution. Okay. So, next example, you take n equals 2 and take omega to be the product 0 1 cross 0 1. Then if you take so you want minus Laplacian u equals lambda u in omega, and u equal to 0 on gamma. Okay. So, now if you take lambda nm equals n square plus m square pi square and wnm equals sin n pi x cos sin n pi y. Okay. Now, this belongs to h10 of this vanishes on the boundary, and you also have delta wnm equals lambda nm wnm because of the variable separable property by example 1. Also, since sin n pi x root 2 orthonormal basis for L2 of 0 1 implies that 2 times sin n pi x sin m pi y is an orthonormal basis for L2 of 0 1 cross 0 1. This standard, this you can prove directly, and therefore there are no other eigenvalues or eigenfunctions because you already have an orthonormal basis here, and therefore you have, these are the only solutions of this. Okay. So, when we wrote that 0 less or equal to lambda 1 less or equal to lambda 2 etc., if n equals 1, then all distinct, because you have n square pi square, these are all distinct, okay, lambda n equals. But in the case of example 2, n equals 2, omega equals 0 1 cross 0 1, then lambda 1 which will be lambda 1 1 which will be equal to 2 pi square, okay, and lambda 2 equals lambda 3 will be equal to lambda 1 2 equals lambda 2 1, and that is equal to 5 pi square. Okay, so and the corresponding eigen, so that means this eigenspace has dimension 2, and the eigenvectors which span the dimension is sin pi x, sin 2 pi y, and sin 2 pi x and sin pi y. So, these are the two basis functions for the eigenspace connected for 5 pi square. Okay, and therefore, when the number of so as so we repeat lambda n as many times as its geometric multiplicity. So, you have 0 less than lambda 1 in this case is less than lambda 2 equals lambda 3 which is less than lambda 4 and so on and so forth. Okay. So, you will have various so equalities amongst these things. Okay. So, now we want to give a variational characterization of the eigenvalues. Okay, so we define for v not equal to 0, v in h10 of omega, we define r of v equal to definition integral omega mod grad v square dx by integral on omega v square dx. Okay, so this is called the Rayleigh quotient. So, we have the following theorem. Let m be a positive integer, then lambda m equals r of wm which is equal to maximum of R of V, V in Vm, which is equal to minimum of R of V, V not equal to 0 of course, V orthogonal to V m minus 1, V not equal to 0, and finally it is equal to min over all W contained in H10 of omega, dimension W equal to m, and max V in W, V not equal to 0 or V, where Vm equals span of W1 to Wm and V0 equal to 0. So, in particular, lambda 1 equals the minimum of mod grad V square by integral mod V square for V in H1 of 0 of omega, V not equal to 0. Okay, so we will try to prove. So, this is called the Rayleigh quotient characterization. It is called a variational characterization because it talks of minima or maxima of the Rayleigh quotient over various constrained minima and maxima. So, the first three are clear what we are saying. The last one, this is called an intrinsic characterization, this min max. The first three depend on the eigenvectors which you have chosen, because the choice of eigenvectors can be of an orthonormal basis, can be different. Then it's not, there's nothing standard about them, because you can choose Wm or minus Wm, whatever you like. So it doesn't matter. But the last one does not depend, it's a frame independent thing, it does not depend on the choice of the eigenfunctions. It says you take any m dimensional space and take the maximum of the Rayleigh quotient there and minimize that maximum over all m dimensional spaces, that will give you the lambda m. So, this is a very beautiful characterization of the eigenvalues, and therefore, in particular when m equals 1, you have that it is just a minimum over the entire space. Okay. So, this is the thing. Okay. So, we will prove this. So, proof. So, minus Laplace Wm equals lambda m Wm. So, this immediately implies that lambda m equals R of Wm. You just have to multiply by W, integrate by parts and then divide. So, there is no difficulty about that. Now, let us take any V in Vm. Okay. So, V can be written as sigma alpha I Wi, I equals 1 to m. Okay. So, if you then compute the Rayleigh quotient R of V, so you must remember that in grad Wi grad Wj equal to 0 if I is not equal to j, and integral Wi Wj is also 0 if I is not equal to j, and if I equal to j, grad Wi grad Wj is lambda times lambda I times integral mod grad Wi square, and here it is lambda is this if I equals j, and here it is 1. Okay. So, this is what we have. So, if you compute the Rayleigh quotient on this using this expansion, then R of V is a straightforward computation. So, this is equal to sigma I equals 1 to m of lambda I alpha I square by sigma I equals 1 to m alpha I square. Okay. And since you are numbering the lambdas in increasing order, therefore, this is less than or equal to lambda m, each lambda I is less than or equal to lambda m, then sigma alpha I square by alpha square is just equal to 1. So, max V in Vm, or rather sup I should say, V in Vm, V not equal to 0 of Rv is less than or equal to lambda m. Okay. But Wm belongs to Vm and R of Wm equals lambda m. So, the maximum is attained, and therefore, that max V not equal to 0, V in Vm R of V equals lambda m. So, that proves the second statement. Now, let V be orthogonal to Vm minus 1. So, this orthogonality we saw is the same whether it is in H2 or H10 or in L2, and therefore, V, in fact, if you write the Fourier expansion, this will be equal to k equals m to infinity of alpha k wk, which is equal to limit of L tending to infinity of sigma k equals m to L of alpha k wk. So, if we set VL equal to sigma k equals m to L alpha k wk, then R of VL, as we saw already, is sigma k equals m to L lambda k alpha k square by sigma k equals m to L alpha k square. Now, again remember we are numbering it in the increasing order. So, the smallest of this is lambda m, and therefore, this is greater or equal to lambda m, and therefore, since VL converges to V, we have that for all V not equal to 0, V orthogonal to Vm minus 1, you have that R of V is greater or equal to lambda m. And Wm again belongs to Vm minus 1, R of Wm equal to lambda m, and therefore, this implies that R minimum of V not equal to 0, V orthogonal to Vm minus 1 R of V is in fact equal to lambda m. And in particular, if m is equal to 1, we get that minimum of R of V orthogonal to V0, that means V in H10 of omega, V not equal to 0, this is in fact equal to lambda 1. So, finally, let W be a contained in H1 of 0 of omega, dimension of W equals m. Okay. So, now then W intersection Vm minus 1 perp is not equal to singleton 0. Why is this so? So, that means that there exists a W in W such that W is orthogonal to Vm minus 1, W not equal to 0. Now, why is this so? Well, W is a m dimensional space, so you need m conditions to specify it. Now, W orthogonal to Vm minus 1 gives you only m minus 1 condition. So, you have still one free condition which you can use, and therefore, there exists a vector like this. Otherwise, you can also do a purely dimension argument directly. W is m dimensional, Wm minus 1 perp must be, therefore, will have at least dimension greater or equal to 1 even if this whole space is inside W, okay, which it will not be, it is not necessary. So, even if the whole space is inside W, its dimension must be at least 1. So, therefore, you have definitely some vectors which you have here. Therefore, max of V in W, V not equal to 0 of Rv is greater or equal to R of W, and since W is orthogonal to Vm minus 1, this is greater or equal to lambda m. Okay. Therefore, min, so for every m dimensional subspace, the maximum is greater or equal to lambda m. So, this implies that min W in H10 of omega, dimension W equals m, max V not equal to 0, V in W of R of V, this is greater or equal to lambda m. But dimension of Vm equal to m, and max of RV, V in Vm, V not equal to 0 is in fact equal to lambda n, and therefore that completes the proof, and therefore this implies that min of W contained in H1 of 0 dimension W equals m, max V not equal to 0, V in W R of V is in fact equal to lambda n. So, we have proved this theorem completely. So, as I said, this last one, the min-max principle, is a intrinsic one. It does not depend on the eigenfunctions at all, and therefore it is a very powerful result, and we will see several applications of this presently. Okay.